Welcome to lecture 18. So what we are discussing, a column under pulsating, a column under pulsating load and compressive compressive load, compression. So consider a column, and then this is, we assume to, for simplification, we assume to be simply supported, and then it is allowed in axial direction to deform. So it's a static component P0 and dynamic component that is PT, right, cos omega t. Omega is the loading frequency. So if you write down the equation of motion, of course that we have done in the previous class, we have to consider inertia and then the stiffness, elastic stiffness, that is given by EID for W dx4, and then because of the axial force there will be P0 plus PT cos omega t multiplied by d2 W dx2, and with the boundary conditions in the hinged end is W is equal to 0, W is the transverse deflection, and d2 W dx2 is equal to 0, right, in both the end. With this thing we assumed that the solution of that equation to be in the form, so Wxt we have assumed to be in the form sin t, and then sin n pi x by L in this form, and then summation of there are number of mode we can consider. When we are assuming sinusoidal, it satisfies all the boundary conditions, right, and then we substituted. So essentially there is a separation of variable in automatically occurring. This is the type. So special part we have assumed the solution, so don't have anything to do with that. We are right now interested in the temporal part. That's what we can see this. Okay. Now what we have seen that, let us define the several parameter, which is we defined the natural frequency to be we can in the previously you can recall that we have defined from there when we are arriving at that equation, please note that I will put N0 natural frequency. So please distinguish between the loading frequency. Omega is the frequency of loading, whereas I am putting, when I am assigning a subscript n, this is the natural frequency. Okay. So here I am going to put that N0, N is 0. Please note that. Okay. So here I am going to put N. I am going to N0, and I am going to put N0, okay, N, N, so N0, here please see that. So we have, please recall that in the previous class we have noted it down. So P critical N was nothing but pi square EI by L square, pi square, of course N square was also there, N square, right, and that was critical loading for the nth mode, and then frequency N0, N0 square was, we have written N to the power 4, pi to the power 4 by L to the power 4, EI by mu, EI divided by mu. Mu is the mass per unit length of the column, mu, right? You can understand that EI by mu. So that's the nice frequency, okay, lateral frequency of vibration. So when I understand, then we have defined all this quantity. Please note that when I am defining omega N0, that is the natural frequency when without considering the effect of axial force. Please note that when there is axial force, there will be erosion in the lateral stiffness, right, that we have all learned. So when I am defining N0, natural frequency, without 0 means it is without considering the effect of axial force, right, that's what it is. However, when we are considering N, that means we have already considered that erosion, P0 by PCR, and do you see that? So natural frequency under the influence of axial force. Axial force is only the static component. Clear? Then I have also normalized the other omega N0 PT by PN, something like this, and here we are defining this ratio, where this is nothing but ratio of the axial magnitude of the dynamic force and divided by PCR critical load minus P0 as a that of course this will be a small parameter, that's why too small. So then all this simplification we have made. Okay, clear? So now with all this simplification, how what this equation will further it will be simplified. I am writing this equation will be simplified as something like this: del 2. Please note that I can replace this del with the capital D because it's a only function of time, so it's a single variable, right? dfn del t2 plus omega square 1 minus 2p cos omega t, fn to be 0. So that is the governing equation ultimately we have obtained. Okay. Omega is the free vibration frequency under axial static load. Omega 0 is the free vibration frequency without static load, and small p is the excitation parameter. Okay, I can write it down. Okay, so omega can we remove this thing, this one, remove these things. Okay, so here please write omega 0 is the natural frequency of transverse vibration vibration without the influence of axial force, without the influence of axial load, and omega n is the natural frequency under the influence of axial force, and small p is a load parameter, small p, this one is a load parameter. Okay, it's a ratio of course, load parameter, but it's a critical parameter, please note that. What you can understand, what it signifies is the extent of the amplitude of the dynamic loading. Of course, it is normalized with respect to this, right? Clear? Now, what I will do, this equation you can, if you see, this equation is a ordinary differential equation, but homogeneous, but it is with variable coefficients. Please note that this is a variable coefficient, right? With a variable coefficient. And also what we see that the loading itself is a parameter over there. Okay, right? Load magnitude itself is a parameter, system parameter. Do you see that? So load magnitude of loading, this PT in the form of a normalized parameter small p become a parameter of the system. That's why this kind of equation is called parametric equation. You understand that? And excitation is called parametric excitation. So these are parametric excitation. Parametric excitation. So this equation can be simplified in standard form, okay, using some modifications that I can show you. Okay, the modification is this equation can be converted, in the standard form. This is called Matthew equation. Okay, this is called Matthew equation. It's a standard equation, Matthew equation, and the solution of this equation can be expressed as Matthew function. A solution is Matthew function. Matthew function instead of Matthew function. Okay, it is Matthew equation and it is Matthew's function. Okay. Now, of course, the standard form of Matthew equation is little different, and we can definitely do that. Just with the scaling of variable. Okay, we can do standard variable scaling, scaling of this time variable. So the way you can do it, define a variable t dot is equal to tell omega t. So the time variable multiplied the excited, omega t. This is a change in the scaling of the time variable. Okay. Then with this thing you can write del f del t is equal to, you can follow the chain rule of differentiation. So del f del t dot omega, and you will see del 2f del t2. I am not doing those things, but you can clearly see this is omega square del 2f del t or square, right? And then if you take and then substituting this equation, if you substitute this equation, you can write omega square del 2f square plus omega square 1 minus 2p cosine of omega cosine of t dot f is equal to 0, okay, or f or fn, whatever you would like to put. And then we can define some parameter a as omega square omega n square, and epsilon to be minus 2p omega n square by omega square. So it is minus 2 small p a. Then this equation can be further simplified to be del 2, what I am going to write f dot here, no, don't require f is fine. So del f del t dot square plus a plus epsilon cosine of t dot f is equal to. So this is a standard form of the Matthew equation. If you go to MATLAB, you can, or any other standard mathematical software, you can get the Matthew function. They will plot it, but then the parameter will be small a and small. This is the standard form of the Matthew equation. Okay, the standard. You can clearly see that this is also Matthew equation. Just a variable scaling. The time variable has been scaled. You understand? So this is called standard form of Matthew equation. Okay, standard form. So when you use any mathematical standard form, fine. Now I can solve this equation can also be solved using perturbation technique. Okay, so we can use Poincare-Linde step perturbation. Here, as you see, since we have introduced it, so we can assume Fn, we can assume asymptotic expansion. So you can understand epsilon to be a very small parameter because p is a small parameter and then omega n square omega. So treating epsilon to be a small parameter and a is kind of a constant, right? So we can have asymptotic expansion for both f as well as omega. You understand? So then, if we do that, then well, for here is this one, yeah. So then using that asymptotic expansion, then substitute in the equation and then equate various orders of epsilon parameter, epsilon to the power 0, epsilon to the power epsilon to the. Please note that here the expansion with respect to small parameter epsilon is already a variable in the system, right? And that controls the degree of nonlinearity. So and then you can get the linearized equation of various orders, epsilon to the power 0, epsilon to the power 1, epsilon square, and then sum up everything to get an asymptotic solution. That is possible to do. But here we are not avoiding that, we are not going to do that. We know that Matthew function will give us the solution. So let us see how Matthew function look like, and from there how we can get the equation, the stability condition. Okay. So for standard Matthew function, I am going to draw it. How does it look like? It is little peculiar. Okay. So I am going to draw it. So you see that the hashed boundary is stable boundary, okay, hashed one, okay, and the hashed one is basically stable, hashed one, huh? Otherwise it's unstable. So you can clearly see that. So my first instability will look like this, let me draw 1 by 4. That's a transition from stable to unstable, right? Then it will occur around 1. Then it will be 2.14. So here stable unstable basically happens in 2 to the power 1 4. So here they need to occur at 1, and here 1 4, 1 4 to 1 to 1 4 is the basically the shifting from the stable to unstable. So this is the diagram is we are plotting the Matthew functions, right? And this diagram has some name is called Strutt diagram. Okay. So higher instability, let us not care. We should concentrate on the first instability. So here, and what we are plotting here essentially, is basically omega n upon omega. That's what we are plotting, square. Okay. That's what, and on the right here we are plotting essentially minus omega n 0 square, omega square, pt divided by p crn. So essentially we are plotting this one. We are plotting this. Now whatever we are plotting, it doesn't really matter. This is important. What we can see that when the first instability is sets in, when omega n, omega n by omega square is essentially, 1 by 4. So what does it mean? That omega n by omega is half, and then omega n is essentially, omega is equal to 2 omega n. So what does it mean? That means, this is the first instability. So first instability sets in, right? Sets. So what is the kind of instability? The instability is, that means, and of course the second one happens when omega n by omega 1, and then omega by omega n 2 to the power 1 by 4, right? A 2 then 1 by 4, okay, the fraction. Now the first one is most important because that's where it is losing instability. So, and what is that kind of instability? Instability means the amplitude will increase what? Unbounded. The amplitude of the vibration will be unbounded. That's the instability here, dynamic instability means. Meaning when you are, compressing the, the column with axial forces, right? Then the vigorous, very vibration, lateral vibration will be way too high, vigorous, right? So that condition, at which condition it occurs, where I can see the frequency of the pulsating loading is twice the natural frequency of lateral vibration, and this natural, this frequency is under the influence of the axial force, static axial force, right? What we can see then, that well, there, this is little different. You see, what we have seen, that omega and the loading frequency has to be 2 times the frequency of the system, right? And this, it's still multiple by 2 times. What happens when omega is equal to omega n? We have learned that this is nothing but omega n is the resonance, right? But this is not, this is also a some kind of resonance, but this resonance occurs in a parametric system. Why it is a parametric system? Because the loading itself become a parameter which is governing the stiffness of the system, right? Because axial force is changing the property of the system. That's why this is called parametric resonance. Parametric resonance. But what is important to note here, you see that under this condition, because we have assumed the axial force to be P0 plus Pt, cosine of omega t, right? So even under that, what do you see? That this can take, if you go back to here, in your when in the expression of omega n, when this vibration is occurring, the magnitude then P0 is greater than PCRN, meaning a column can sustain load beyond critical load. Okay, parametric resonance, when it is occurring, the system can, because it's even P0 can be greater than critical load. But in addition to that, you are getting some component of dynamic load. So it can be higher than critical load. So parametric resonance, when it is occurring, it may occur at load beyond critical load. So column can sustain the loading amplitude which is beyond critical. You understand that? Of course, a part of it is static and a part of it is dynamic. Okay. So what we see, so this kind of instability occurs parametric resonance when the axial frequency is 2 times than that of natural frequency of lateral vibration. That condition you must recall. Okay. We will try to establish the same thing using a different approach, using energy analysis. So you understand the Matthew equation and then what is Matthew function, what is the parameter in it, and how the stable and unstable boundary is basically being distinguished, and we have identified the point at which the transition from stable to unstable boundary occurs, right? We will try to establish the same thing using a different consideration, using simple energy analysis, and that will be more intuitive to understand what is really happening. Okay. Here, please note that in this, we didn't consider the effect of damping, but effect of damping can be very easily included if we consider the energy analysis. So I am considering here inertia, of course, over there. Now I am considering damping, right? We will consider subcritical damping. So this is we are going to do energy analysis. So you see that here, what is the input energy to the system? So this load P0 plus, that is working with what is the deformation U, axial deformation because of out of plane displacement. This is what integration of course W is a function of x and t, please note that. So what we have assumed, W is equal to f t and then sine n pi x by L, right? Well, let us assume that Wt is basically some amplitude, maybe small a sine omega. I am assuming this is sine, okay, little different from the previous. This is the expression for W, function of x as well as t, right? So then integrate it first to get u. Of course, what you can see here, that u will be a function of t here. So then if you integrate integration 0 to L, a square sine square omega t and pi by cosine square pi by L dx, right? And then here it is pi square by 8L and 1 minus cosine. Please note that here, just for simplification, we consider that, well, the so this is P, so listen, so 1 minus cosine of 2 omega t. So what is the work done? So please have this expression, okay? So we got ut and then ut as pi square a square by 8L 1 minus cosine of 2 omega t. Yeah? Use the axial displacement along x. So now with this, what is the work done? Rate of work done? Work done over some cycle by the axial forces. What is integrate it? Of course, W as a function of T work done. W as a function. Of course, here you see that this is small w. This you can take a small w, capital W. Okay, or maybe work done D. I am taking it will be integration P, and what is the power? Force into velocity, right? Velocity means du T by dt, right? And then you integrate the energy, then you will get the power, right? You will get the total energy input. So work done by the axial force or energy input by work done by the axial force, or it is the input energy, input energy over a cycle, over something. So if you integrate, then integration 0 to t, and this is p0 plus pt cosine of omega t du by dt is pi square 8L, and then sine 2 omega t. So if you integrate it and things, then you will see that pi square. I am simplifying this expression. You integrate it omega 8 by 8L, and then pt integration 0 to t cosine of 2. Yeah, please note that this is excitation frequency, and this, when I am assuming this should be a different frequency. Okay, so I don't know what I should assume. I should maybe I will put it omega cap. I will put it omega n. Okay, omega n. Okay, omega n. Omega n, please. On pt cosine of 2 omega minus 2 omega n minus omega into t minus cosine of 2 omega n plus omega t dt plus p0 by omega 1 minus cosine of 2 omega t. So what we see that this is under integral. Now see, please notice this integral is interesting. Please note that see, this will all give the periodic solution. 1 minus cos 2 omega t is nothing but 2 sine square omega t, right? It's a still it's a periodic function, right? 2 omega n plus omega, whatever be the thing, ultimately cosine means it's a periodic function, right? Now consider a situation in which 2 omega n is equal to omega. Then what will happen? Then it's a cos 0 means 1. So 1 meaning sum multiplied by dt. So it's a function of t. If we integrate, so if beta become a function of t, do you understand? Function of t means with increasing time it will build up, right? And it will give the unbounded energy. So from this, and if the input energy, so the work done here essentially, that is basically giving input to the system, right? That work is being stored as a strain energy here. Or because it is happened dynamically, we are considering that it's a kinetic energy input to the system. So if a system cannot take unbounded energy, kinetic energy, and it will lead to instability, and that's what we can see, because so from this energy input, do you understand how what is the condition of instability? Condition of instability is 2 omega n is equal to omega. That means once again, if the excitation frequency is 2 times the natural frequency, then it is leading to unbounded energy input to the system and instability. And this is same as the condition of parametric resonance. It is identical to the condition of parametric resonance. Parametric resonance. This is much simpler and much intuitive way to say, right? Now let us, because here in earlier cases we can find out some condition that how to dissipate this energy. Of course, previously we didn't consider damping because we didn't have any mechanism to dissipate energy. But right now, if we consider viscous damping in the system or any form of damping in that matter, but viscous is the simpler one, okay? So then that we will see that how much energy that is dissipated by damping, viscous damping, and then we can arrive at a condition of stability. It's not that only, okay, so let us do that. So keep that in mind, this WD, this expression, okay? And now, what is the energy dissipation due to damping? Would you please tell me? Well, before that, we can do some simplification. We can assume that you can see, instead of making it in terms of t, we can consider a number of cycle, okay? And then we can count the input energy and can make the integral definite instead of unbounded. So let us consider, integrate it, consider t as pi by omega. It's a half cycle into n. N is the number of half cycle. N is the number of half cycle. Then you make the integral definite omega d as a function of half cycle, t. Then you will see that if I write down the expression, then pi square omega divided by 8L Pt into Tn. Tn is nothing but time duration of non-Pt. This is the input energy. Okay, now. So why this is so? Because we do not, working with the integral is a little cumbersome. So let us consider the number of cycles. Doesn't really matter. We can count how many cycles it will be stable, and after that instability will set in, right? So the dissipation by viscous damping will be what? How? Of course, here I will integrate. What is the dissipation? 2 xi. Xi is the critical, damping ratio. Xi is the damping ratio. C by Cc, critical ratio of damping to damping coefficient for critical, right? So 2 xi m is mu omega. This is the C, and then the what? dw upon dt, right? This is the expression, right? See, damping force, damping force due to damping is what? C into U dot, right? C into W dot, C into dW dt, and C is nothing but 2 xi mu omega n dW dt, right? So this is the damping force. This must be multiplied with the respective velocity. So this will appear in square, right? And then if we integrate, of course, over the L dx. So substitute it, integration 0 to t, integration 0 to L, 2 xi mu omega n, omega n square omega n square cos square omega n t, and sine phi x upon L dx dt. So is equal to 2 xi mu square sine 2 omega t divided by 2 omega. And then you can substitute, once again you can substitute t is equal to Tn, and then you can find out, So if you substitute t is equal to Tn half sine, so t is equal to Tn, then this is the sine 2 omega t will be, sine 2 omega, t means, pi by omega into n, omega will cancel out, so 2 pi n will be always 0. So 2 xi mu omega into Tn. You can write it, right? So over each cycle, okay, then omega xi at t is equal to, by n by omega n, this will be, 2 xi mu square omega n cube L by 2, and t is pi n upon omega n. This is the other one which this is. So of course this and this need to be balanced, right? This must be greater than that for the stability, right? So for condition of stability, if we want to derive the condition of stability, this is dissipation, this is input. So condition of stability will be, condition of stability. So by, if you, you can see that, damping must be input energy, So here, if we simplify, substitute all the expression, I am writing the final expression. Okay, the final expression will be, Pt divided by 2 Pcr minus P0 less than 2 xi by omega n. That is expression, Cr, of course, P0 greater less than P Cr. So now this is for simple damping, you can see this is a ratio, right? Pt by Pcr. So this is also a small quantity, and this is also a small quantity. So this balance need to be. This is for viscous damping. So ion. So you see that this expression is for viscous damping. You can exploit superelastic damping too for stabilization. That's why you can put a superelastic wire, and then of course there this expression will be more complicated. Okay, but you have to do that. Okay. So one thing. So what we are considering all in the follower force, etc. There is a non-conservative force, but please note that a follower, just because the force is follower doesn't mean it is non-conservative. Okay. For example, if you have a column here, okay, and you consider this column, this column, and it is maybe it is fixed with something, fixed with some another support here, okay, support here, and then so basically causing the force to be always passing through this, but this is not an example of follower force. So what I mean is that a force which is directed in a particular direction, doesn't mean that it will be non-conservative. This is not a case of conservative force. Follower force is a non-conservative force, but this force is this is not non-conservative. Okay, not a non-conservative example. Just because the force is following the direction doesn't mean it is here also. You see, if it is anchored and then deformation, along with deformation, this fellow is following that, it is non-conservative. Similarly, another example is if you have consider a cell and then it is subjected to hydrostatic forces. Okay, so hydrostatic force means it's always perpendicular to this, right? So whenever it is deforming under this force, whatever little deformation occurs on thing, it will also be perpendicular to that, right? So you may think that, well, this is also a follower force, right? It is always perpendicular because it is following the deformation pattern, deformation of the surface. Hydrostatic forces are always perpendicular to the surface, right? Isn't it? But do you think it's a follower force? It's a non-conservative force? No, it is not a non-conservative force, because this kind of force you can see, and it will not cause any instability in that matter, because this cannot pump infinite energy to the system. This deformation will still be finite. Okay, as soon as it attain equilibrium, it will stay in its place. So this is also not a example where instability will occur. Okay, fine. However, if we consider a cell, spherical cell or any cell that matter, and it is subject to the aerodynamic force, and the aerodynamic pressure is moving, the flow, air is flowing, then it will cause instability. Why? Because that's a continuous source pumping of energy. Then that time it becomes conservative, but not for a pure hydrostatic case. So please distinguish this case with a case in which there is an and this is subjected to aerodynamic forces, some airflow. Under this airflow, this will cause instability, flutter and other things. Okay, that I will come later. So this is a non-conservative. This is a non-conservative example. This is not. Similarly, I will also demonstrate to you some example in which just because force, magnitude, force, direction is maintained. So these are the example in which the force are changing their direction on the deformation of structure, following the deformation of the structure, but they are not non-conservative. Similarly, also it shouldn't be driven with a false notion that just because force is maintained, the direction of force is maintained constant, it is not, it doesn't ensure that it is a conservative system. I will show you this example. So just because forcing direction, forcing direction follows the deformation of the structure of a system, of a system or elastic system does not mean it is a non-conservative conservative system, which is given by here. Conversely, just because the force is maintained its direction, does not mean that the force maintains its direction does not mean that the system is conservative. Give you an example of the second kind. So this is very interesting system and often encountered not in civil engineering practice but in mechanical engineering. So you have seen the shaft, right? The shaft, which is of course this will also, there will be bearing, and this is subjected to torque, right? And it is under axial compression. So what will happen? This example, this is a typical example which is a non-conservative. How it is so? Let me explain to you. So I am considering the situation. So I consider a shaft like this. Okay, so it will have something like this. This is a deformation. It is subjected to axial force P here, right? P, and then it is also subjected to this kind of torque M, or T, torque T, and it is moving, right? Torque T, So then what will happen? So if consider, you have to consider the section, and then you consider its, of course, when you want to study stability, you have to consider the equilibrium equation in the deformed configuration. So I am considering the equilibrium of this in the deformed configuration, this shaft. Okay. So what I am going to do, now, so axially loaded shaft, axially loaded shaft, and this is also called gyroscopic system, gyroscopic system, this gyroscopic instance. So then, if you consider that projected in the xy plane, so if you project, so you can clearly see if I draw a tangent here, the x-axis will change right here, right? X-axis will change. So this is the x-axis x dot, and this is the y dot, right? Isn't it? And I am defining, this is the torque. I am defining with in this diagram, arrow diagram T. And what is this angle? This angle is what? Along y direction. I am assuming the deflection along y direction will be, is Wy, and deflection along z is expressed as Wz, right? So if it is deflecting along y, this angle is nothing but Wy by del x. dwy del x. Okay, so this angle is something like that. Now you can see this is nothing but t cosine of this one, t cosine of dwy dx. It is basically t dwy by dx, right? Sorry, cosine of this thing, how can it be? Cosine is small, it is equal to t, right? If it is very small, it's right. And then there is another component here, that component. So this component is the torque, right? And this component will be bending, right? This component will be what? T sine dwy upon dx. So I can write t dwy dx, right? This is the bending component, na? So now if I write down the equation for this, in this plane, of course this is called bending. So this is with respect to y axis, right? So may I write this equation to be ei. So the deflection is happening in the y, deflection is going to occur if it is along y, deflection will occur along z direction, right? If the bending with respect to y axis, that will cause deflection what? Along the z axis, right? So that's what eiy d2w z by dx2 will be equal to, so this is x will be equal to, this is y, t, right? Y, huh? Will be equal to t dwy dx, and then along with that, because of the axial force, there will be additional bending moment p into wy, right? If the deflection is along z, it will be pwy, right? Pwy. So this is the component of torque that is contributing in bending, and then this bending with respect to z axis, so deflection will be along y, right? So this will also be pwz, is the same, okay? This will be one equation, okay? The other equation, similarly, if you consider and project it over the z, okay, then you will get, similarly I will project it over the, instead of xy plane, I will project everything in the xz plane. And in xz plane, you will see the equation will be ei z d2w y dx2 will be t dwz by dx minus pwy. Equation 2. In one case, what will happen? In one case, if on this torque, this bending we are considering, right? So in one case, if it is in positive, the bending moment, if it is along positive, positive y axis, positive y, then in other, when you are projecting along xz, that will be along negative. So see, m is equal to what? M is equal to ei d2w dx2 is equal to m in one case, if the curvature and bending moment is along same, right? Otherwise it is minus, right? So with one choice of coordinate, you will get ei d2w dx2 is equal to m, whether in other it is minus, okay? So this is in this condition will cause a situation in which one of them will be positive, whether this, in both the cases, this will be negative, one of will be negative and another will be positive, okay? So now if I combining these two as the system, then what I will write? So that basically nothing but the choice of coordinate system and the, so in both the equations, if I write, it will look like e iz d2wy dx2 plus, if you take it right hand side, plus t plus t dwz by dx plus py is equal to 0. In the other case, it is eiy d2 wz to minus m minus t d2 wy dz plus p is equal to 0. That you will, this kind of system of equation you will get. The interesting part here is that, so let me explain to once again what is happening. So, you have your column, your shaft, that is subjected to torque and it is subjected to axial force also. We have considered its deformed configuration. When we are considering in deformed configuration, if I cut a section, I will take it deformed configuration. If I resolve it into component, whatever is the torque, I resolve it into two component, one and considering the deformation to be small. Even in the deformed configuration along x, whatever the moment, that will be basically torque, right? But in with respect to other, axis, whatever is the moment that is coming, that will be bending moment. So that bending, the component of that two bending moment we have, of course, we can clearly understand that there will be one bending moment component because of the deformed configuration along z and along will be one will be along y, right? So that we have considered, and then we have right, and then there will be another component that is coming because of the axial force. Because of this deflection, it will also contribute in moment P into W, right? So in both the cases, the total bending moment we are taking and we are writing down nothing but the bending equation. M is equal to Ei d2 W dx2, right? So when it is bending with respect to z axis, then of course with respect to y axis, then the deflection is along z direction, right? So Ei d2 W dz2 dx2, that is fine, and then P into z, right? That is the contribution, and then this is the component of torque that is contributing the moment. However, in one case it is negative, one case it is positive. Why this is happening? Because if we project in x, y and xz plane, in one case the bending moment and curvature will be in the same direction, and in other cases it will be opposite. Okay, that's why this negative sign will come. Clear? So all these details I am not going, but I will write down the equation here, right? And when I am writing down the equation here, then you can see this is the linear simultaneous equation, right? Two differential equations, simultaneous differential equation. The important part is that Wy, and it is space, there is no time involved here. It is all static analysis. And Wz, we can assume the solution to be y0 e to the power lambda x, and here W0 e to the power lambda x. And we assume something like that, and you substitute it here. You assume this solution and then substitute. If you substitute, then you will see that I have done it, and I will just write quickly to save time. This will lead to an equation of something like that: lambda square Wy0 plus T by Eiz lambda Wz0 plus P by Ei z Wy0 is equal to 0. In other cases, it will be lambda square Wz0 minus T E I y lambda Wy0 plus E by E I y is equal to 0. So here, from here, what we see that lambda square plus please note that equation. Here there is very interesting part. The interesting part is that you see this led to essentially what? An eigenvalue problem. So homogeneous, right? But there is an interesting thing here. If we take this to be a stiffness matrix, of course it can be a stiffness matrix, right? The way of, and it, I mean, knowingly or unknowingly, we have considered that what is the part of mental stiffness matrix, because there is E, I, Z, all this term is there, and geometric part is nothing but P, right? Do you see that diagonal terms are positive? I mean, well, you know, lambda square, this whatever, but of diagonal terms, do you see that here it is, you know, sorry, of diagonal term, you know, these are asymmetric. Do you see that? Have you seen the stiffness matrix to be asymmetric? Stiffness matrix are always symmetric, right? Point stiffness matrix can be asymmetric. Positive stiffness matrix, conventional stiffness matrix has several properties. One is of course positive definite, another one is need to be symmetric. Why? Because of the Betti's reciprocal theorem. If there is a positive energy flow and on deformation, if you will apply load at I point, whatever deformation jth point, if you apply load at jth point, deformation should be same. Why? Because there is a positive energy flow from I to j, then there is the same energy from j to I. When it is asymmetric, asymmetric stiffness matrix occurs several cases. The follower force, whatever I have solved, if you cast it into finite element equation, I will tell you how to do. Then you will see that that will lead to a asymmetric stiffness matrix. Here also asymmetric. So asymmetric stiffness matrix is a manifestation of the fact that the system become non-conservative. The system is non-conservative. This kind of situation also occurs when the system, when a 3D continua is subjected to damage. In damage mechanics, you will see sometimes it, because of damage, it loses its this symmetry. And another case in elastic system is the non-conservative. So this is a asymmetric stiffness matrix. I don't know in finite element whether you have studied the problem where there is a fluid flow, flow in a pipe, or one-dimensional convection, convection and the species transport. So there is a flow, and you are putting a drop of ink there. The ink will flow from this point to that point, the direction of flow. Will the ink be ever come from that point here? No. You understand where the reversibility is broken? So the direction of flow basically governs. Now that, I don't know whether you have solved that, that equation, if you can recall, that will also give a stiffness matrix which will be asymmetric, non-symmetric. Convective transport of species, and this is also as mathematical, there is a very elegant mathematics. This is called non-self, this problem is called not non-self adjoint problem. All these problems which are having symmetry are self-adjoint problem. You can have an adjoint defined for the system, but for the asymmetric, it is, there will be this non-self-adjoint, okay, non-adjoint, okay, non-adjoint. There are mathematics. Please read little bit about it, okay, about those of you who are taking the optimization, you might have done that. You find in dynamic stability also for a system we also find out self-adjoint system, okay. But so now when you will solve this, how many if for the characteristic section, determinant of this will vanish, right? The determinant will vanish of this system need to vanish. Then what does it give? This gives a characteristics equation, and that equation will give us the eigenvalue on solving. Now that the characteristics equation, by making the determinant 0, characteristics equation, this become lambda to the power 4 plus lambda square p by e I ij plus p by e I y plus p plus m t square plus t square. T is the torque, t square by e I y e I z plus p square by e I y e I z is equal to 0. This will give a set of eigenvalues and eigenvectors, right? Now with P, you have to see the variation of lambda with P, of lambda with P, the axial force, P and of course torque. So there is two control parameter P and T, and then you can define the stability boundary. You can clearly see that for a valid solution, if lambda is, of course, because of asymmetry, it will be complex, it will appear in complex conjugate, right? So, and then the complex conjugate real part should be negative and then imaginary part, okay. So, depending on the situation, some places it will give a stable solution, some places it will give an unstable solution. I will discuss for this problem how you have to play with the sets of eigenvalues, so to decide that whether it is stable or unstable. That I will discuss next class. But you understand that you will get eigenvalues from the characteristic equation, and those eigenvalues will appear in complex conjugate. If A plus IB is a eigenvalue, then A minus IB also a eigenvalue. Okay. Now this will give you sine and cosine time of solution. That's fine. That's perfectly well stable. A will play a role. A has to be negative for bounded value. But if B is, not positive, or B vanishes, then it will not give a stable solution, right? All these things we will discuss. But what I want to point out for this system at least is that here you see the case in which load is not changing with its deformed configuration structure. Yet the system is non-conservative. So non-conservative loading can be identified for physical consideration, whether it has potential to pump up enough energy, unbounded energy, or secondly, a very good example mathematically to check is the asymmetry of the matrix, system matrix. Clear? Thank you for today.